Hello friends, my name is Devajyoti Go. We are a group of 6 friends who run an undergraduate practical lab in College Street, Kolkata for Calcutta University students. We are called Delight Physics Lab, or DPL in short. We have been running for 3 years now, and we are really happy to say that this is the first time we have thought of making an YouTube channel to show what we teach our students and to make our work more accessible to them. So this is our first YouTube video, and today we are starting with a practical which is quite feared by the students, third year students precisely, but is one of the easiest practicals as per our view. So today we will be sharing BH loop, as they say, but that's not the real name of the practical. We will discuss what the actual name of the practical is. So let's start. Okay. So my target audience is basically Calcutta University students. So I'll be speaking mostly in English, but at times I might talk in Bengali. But if that is inaccessible to some other language speakers, they can always comment below in the YouTube video and I will be answering your questions. Anyway, I'll try to speak in English first. So what is the practical's aim? The aim of the practical is to find the hysteresis loop of a given ferromagnetic material. The material is usually in the form of a ring. We call it anchor ring due to historical reasons. Our job is to find how magnetization of that ring changes with changing outside magnetic field, external magnetic field. And as we know, it will form a loop that we will see. I'll be talking about the theory of it. So that's basically our job. But sounds easy. You will see that due to several practical problems, such a simple thing that we read in theory is a bit complicated to do. But if you are remembering everything that might happen theoretically, then I will say that this is not much tough a practical to do. So let's see without further ado. At first, I will be talking about the theory of the practical, what we are trying to achieve. Okay? You will see when you go to do the practical, there will be an anchor ring, as I said, that is circular in shape. You can say toroidal in shape. It's a ferromagnetic ring, an anchor ring. It's called anchor ring due to, as I said, historical reasons. They are used to hold the anchor of the ships below the sea. Anyway, that's not important. Now, the coil is in a form of a toroid, turned around it in a very tightly packed manner, say N1 turns. Okay? So, if the mean circumference because that's what we use in generally, because we want to find the magnetic field exactly inside the anchor ring. So that's why you are using the mean circumference. If this diameter is d, if this mean diameter is d, then the mean circumference is pi d. Then this will be the number of turns per unit length of that toroid. And as you know, this term will be important in finding the magnetic field inside. If the ferromagnetic material has a has a magnetic permeability mu, permeability of that material, okay, it's not mu zero, it's mu, then we know that the magnetic field that will be induced inside is nothing but mu N1 times the current that is flowing through these coils. Right? Okay. There will be one anchor ring, as I said, and in this same setup, there will be another magnetic type of thing which is not made up of magnetic material. It is called a standard solenoid. That is, it is in form of a long solenoid. Okay. Inside it is nothing, no ferromagnetic material. It's air core, and this is one of the reasons it is called standard. Another reason why it is called standard, and actually speaking the main reason why it is called a standard solenoid, is because it is long. Why is that important? Remember from your physics theory classes that these formulas, mu and I for solenoid, we know this similar formula, something like this. These all work inside the magnetic, inside the material only when the solenoidal wire is infinitely long. So infinity, what is kind of a comparison between two things. So it is infinitely long with respect to what? With respect to where the flux is going. So if the secondary is very closely packed in the center, then here the magnetic field must be uniform and straight and of this value, and for that reason our primary has to be long enough with respect to the secondary. And you can calculate this at your own leisure. How long is long enough? That is, say 99% of this formula will be followed when secondary is this smaller than primary. So you can do these calculations. It's not much tough, and you will find it in many books. Anyway, I'm not going there. So it's a standard solenoid because it follows this standard formula. Okay. Let me come into more proper terms. Let me call the number of turns of the primary of the solenoid. Primary of the solenoid, its number of turns be N2 or N3 suppose. Why N3? Because N2 will be needed here also for my own secondary of the ampere ring. So let me call primary of the solenoid as N3. As you know that this N is nothing but N3 by the length of the solenoid. Okay, so this is number of turns of the primary of the solenoid per unit length, and this mu0 is permeability of free space because this is air core, and this I is the current flowing through this standard solenoid. Okay, there will be a secondary of the solenoid, and that secondary might have N4 number of turns, say. That's all I need. So you will have two materials where this flux linkage is happening from primary to secondary. These primary and secondaries are electrically insulated from each other. They are magnetically coupled, as to say. So that's all. Basically, these are the two elements that you will use, and due to one small difference, that one is magnetic core and another is air core, there will be quite a bit of difference in how you handle these two differently during the practicals, and that is all that you have to remember. So let's see. Please remember these terms, N1, what is N1, what is small n1. Okay, I'll be needing them later. Okay, fine. What else do we need to know for this practical? Well, I was not being completely truthful when I said only these two elements need to be understood. There is one more thing in this practical that needs to be well understood, and that is ballistic galvanometer. Now, I will make a separate video for understanding ballistic galvanometer's theory, and I will be linking it very soon. So please don't panic. Right now, I can say only this much about ballistic galvanometers, that they are galvanometers that works for transient current and not for steady currents. Normal galvanometers that you use every day, they work for steady currents. You give a current, say I, they have a moving coil and there are two permanent magnets on two sides. When the I current passes through it, it gets a torque due to these permanent magnets, and that torque can be seen through the pointer reading. So a steady current provides a steady reading, right? But a transient current, it will just pass through it, and it will just get a deflection, and then what will happen? It might oscillate. That's what ballistic action is basically, and I will talk about that in the next video. Right now, all that you need to know is that ballistic galvanometers works when the flux changes. As I said, transient current. So if there is a transient current in the primary, Or say if there is if the primary current is changed from I to some other I, then the magnetic field linked with it will change from B to some other B. Then in the secondary, where the galvanometer, ballistic galvanometer is usually connected, the flux linked with the secondary will change, and due to this flux change, the ballistic galvanometer will get a push and it will start oscillating. That's all. Okay. The rest of the theory you will learn in that separate video. If you haven't seen that video yet, please go and visit it. Okay. What are the equations of the ballistic galvanometer? It's very simple. As I said, for a steady current, you will see in that video that for a steady current, the amount of the pointer deflection theta is proportional to that steady curve of the current. For transient currents, you will see that the deflection is proportional to the flux change. Okay. This flux change is actually proportional to the amount of charge that flows in the secondary, but right now you don't really need to know that much for this practical. You can just remember this much. Okay. So whenever you are learning about any practical that has ballistic galvanometer with it, this is what you will need. You need to understand that the flux change affects the throw. Okay. So let us get into the details of this practical. And for whatever I said right now, please see that video which is on ballistic galvanometers. I will link the videos link in the comment section or maybe in the description. Okay. So as I said, that in ballistic galvanometers, the deflection is proportional to the change of the flux. Now, what is the exact formula? You will see that the exact formula is this. What is this R? This R is the total resistance in that ballistic galvanometer circuit. In that circuit alone, the total resistance might include resistance of the secondary, resistance of the galvanometer, resistance box that is kept, and any other resistances in the wire or anywhere. That entire resistance put together is this R. So you will learn very soon in that video that the deflection will depend on this. That's all. And this is all that we are going to need. What else do we need is exact formula. How this is linked with theta is something like this. The flux change by R is equal to, this is not yet the exact formula, there was still some constant missing, so actually I should have written like this still. The exact formula will be flux change by R is equal to T by 2 pi, where the T is the time period of oscillation, natural oscillation, free oscillation without damping, okay, into C by N A B, where C is the torque constant of the wire on that torsion wire on which the inner coil is hung. Okay. N is the number of turns of that inner moving coil of the galvanometer. A is the area of cross section which is linked with the magnetic field of the permanent magnets. You will see these details in that different video. T by 2 pi into C by N into this theta into 1 plus lambda by 2. What is this lambda? This comes from actually a term which is something like this. it's a Taylor expansion to the first order. So what is this? The details will be in a separate video. You can right now understand that this is a decrement constant, a logarithmic decrement constant. What happens is there is still some damping. Even if we reduce all air damping and everything, there will be still some damping, which you will see for some other reasons. And the galvanometer gets damped very soon. That damping constant, that exponentially damping constant, is called lambda. I will talk about it later in some separate video. So this is the formula for any practical that has ballistic galvanometer in it. In fact, in this practical, we will be changing fluxes. So this term will actually affect how much the deflection happens. The rest of the constants we can put together, call them as K, and they will all vanish. And how will they vanish? It's obvious. We'll need another equation for them to be vanished. So if we do the practical first with the anchor ring, then we'll get something like this, and then we have to vanish this K. And in fact, don't you think this R should also be vanished? Because this R contains of things like the galvanometer's resistance, the resistances in the coil, and several other resistances that I don't know of. I'll never be exactly able to measure this R. Okay, and so this should also vanish. So all this can be vanished only if I have one more equations where I have to do the same ballistic action so that the same type of equation comes. That we do with the standard solenoid. So that is where the standard solenoid comes in. It is just to remove all these constants. You can call it's like a calibration process. Okay. So that's really why you need two things here in this practical. The practical is to measure the hysteresis loop of the anchor ring. You need the solenoid just to remove these from this equation. That's all. So that you have finally an equation where the flux changes is connected to the theta. That's all.
Thank you for watching my video, and share this concept with your friend, and like and subscribe my YouTube channel. Thank you.